graphing with our transformations. So, the reason this wasn't part of our transformations unit is because the parent graph, here's the parent graph, y equals 2 to the x. There's a million parent graphs, because I could change the base. So to keep things simple, we just use it as a review. We could do it in this unit. So first of all, if I want to sketch the graph of the new one, off to the side, I think about my original graph. I label the point 0, 1, 1, 2, and an asymptote at y equals 0. This is my parent graph of 2 to the x. And I want to graph y equals 3 to the negative x plus 2. So first of all, and I'll do this one in green. Anything that is where the x was is always horizontal. Anything outside the function is always vertical. That's exactly the same from our very first unit. We also have to remember that when you have a horizontal reflection and a horizontal translation, that you have to first write that in factored form. So I got to factor out the x, making this x minus 2. Because you see that plus 2? You may think 2 to the left, but it's actually a minus 2, and it's 2 units to the right. Now, if my parent function, I'm going to take out my highlighter here and say my parent function is a 2 to the x. This is also another reason we didn't do this in our first chapter, because our parent function has a number in it. Most of your other parent functions didn't have, let me say, regular size numbers. Like you had an x squared graph, but the squared was a little. So it felt like it wasn't really a number in the same way. Square root graphs didn't have numbers in them. 1 over x graphs didn't have numbers. Absolute value graphs didn't have numbers. This can sometimes get confusing because you will want to break some mathematical rules. So let's go first, let's clear up all the things that will tempt you. Okay? The first very tempting thing that you will see in this question is a 3 times a 2. And it's going to take everything in your body to stop yourself from saying that's 6. Why can't I just change that 3 times 2 to a 6? Do you remember BEDMAS? When did you do BEDMAS, order of operations first? How long ago was that? Grade 6, 7? Oh, just do that. Did I just do that? Okay. So, order of operations. You can't multiply that to get 6. Because the exponent has to happen before we multiply. So this has, that 2 has an exponent. That has to happen first. Now, that's going to be one temptation. The other temptation is you're going to want to say, oh, there's a 2. Should that be a vertical stretch? No. Because in my original function, I have an x and a 2, and I'm going to highlight them there. That's your parent function. Everything other than the 2 and the x is going to be transformation. So if we label our transformations here, this is outside. This is going to be a vertical stretch. We're going to multiply our y values by 3. Here we have a horizontal reflection. X is going to get multiplied by a -1. And here we have a horizontal translation. The -2 will go 2 to the right. And we're going to use the same strategies that we did back in our very first chapter, in chapter 3. We're going to take our original points, which were 0, 1 on our blue graph, and 1, 2. We're also going to take our asymptote. We do stretches and compressions first, then translation second. Remember doing this? It's been a while. So our y values are going to get multiplied by 3. our x values by -1. So what's going to happen there? This will be 0, 3, and -1, 6. And then we're going to go 2 to the right. This will be 2, 3, and -2, 6. And our asymptote at y equals 0, because it's at 0, multiplying it by anything, x values, y values, doesn't matter, will not change it. The only thing that's going to change an asymptote that is y equals 0 is if you move it up or down. So in this case, I'm going to just say, I'm moving to the right. That's not going to change it. My asymptote is still going to be at y equals 0. And I'll actually start my graph with that. Draw my asymptote first at y equals 0. Then I need to label the points. I have a point at 2, 3. And I have a point at -2, 6. So I keep the same shape. And I have my new graph. Now it asks us to answer a bunch of things. Is it increasing or decreasing? The green one is now decreasing. Intercepts. Okay, I don't have no x-intercepts. Did I make a mental math mistake somewhere here? Feel like some.
-1, 2 to the right.
2 to the right. Thank you. I was like, somewhere there's a mental math mistake. -1, 2 to the right. Wow. Should be a positive one. So So how did I discover I made a mental math mistake? Something was going wrong. Well, when I went to find my y-intercept, you can find a y-intercept by plugging in 0 for x. I looked at my graph, and my y-intercept was somewhere between 3 and 6 when I looked at my graph. But when I plugged in 0 into the equation, 2 squared is 4 times 3 is 0, 12. So all of a sudden I was like, that doesn't match up with my graph. Where did I make my mental math mistake? Equation of the asymptote is still at y equals 0. Domain is everything. And the range is y is bigger than 0. So I'm going to add some more graphs to this. So do you have space on page 346? Let's add a couple more graphs. Just to give us some practice. I'll write this one in factored form already. This looks like a very complicated graph. Again, you can't multiply the -5 times the 3 because of exponent laws and orders of operation. Okay? The first thing you have to recognize is what is the parent graph? In other words, what is the base of the exponential equation here? It's a 3 to the x graph, which is really quick to label. And if I take my highlighter out and I say, the 3 to the x is my parent graph. I'm going to highlight the 3 and highlight the x. Everything else in that question is a transformation. In fact, we can go through now left to right and label things. Do you see that this is a vertical reflection and a vertical stretch? You would multiply your y values by -5. Next, we hit the 2. At 2, horizontal compression. X is going to get multiplied by 1/2. Left or right with 4? 4 to the left. And up or down with -7? 7 down. So we take our original points, 0, 1, 1, 3, and our asymptote. Stretches and compressions first. So our y is getting multiplied by -5, our x by 1/2. 0, 1/2, -5, -15. Then we're going to go 4 to the left and 7 down. -4, -3.5. 7 down, -12, -22. And the only thing that's going to affect your asymptote is the fact that you're going down 7 units. So when we go to graph this one, actually, I'm going to cheat a little bit here. I just looked at my numbers. There are a bunch of big negative y values, so I'm going to make my axes more like that. First of all, I'll start with my asymptote. It's at y equals -7. Then I'm going to plot my points. I have a point at -4, -12. I'm going to just sort of estimate. -4, -12. And -3.5, -22. Towards the asymptote, that would look like this. And today I'm going to, for some of you, maybe some of you know this already, but for some of you, I'm going to introduce to you a new number that you have never seen before. Whew. And the new number, it's like, if kids from elementary school were here, they would say, okay, high school kids have gone crazy. The new number is E. How many of you have heard of the number E? Okay, let's first, the letter E. Show hand. Okay, good. Good. Lots of people have heard of the letter E. But the number E. It's on your calculator. See if you can find it. See if you can find the number E on your calculator and push enter. If you found the right number E, that's what it's equal to. Have you heard of the number E equal? No. Okay. Did you find it? Right? I just need you to find it so you don't feel like, is this another thing that Mr. JR is just making up in the middle class? It's actually a number. It's a very important number for calculus, and will be a very important number for this unit in logarithms. y equals e to the x. Oh, look at, I did a question with my calculus class here, and I included the number e in it. So we can graph e to the x. And it's exactly the same as graphing 2 to the x, 3 to the x, 5 to the x. You have 0, 1, and when you plug in 1, you would get 1, e. And you'd estimate that to be around 2.7. And we could also do transformations. You might be asked to graph y equals 3, e to the x minus 2 minus 1. So e to the x would be your parent graph. And your y value would get multiplied by 3. You would move 2 to the right and 1 down. And when you multiply your y value by 3 and your initial point was 1, e, when you multiply by 3, you just get 3e. And then you have to subtract 1, you just write 3e minus 1. And when you go to graph that, well, if e is 2.7, 3 times e is going to be about 8.1 minus 1. So when we go to graph, we just sort of estimate those values. And for those of you who are like, why do we have the number e? Like the number e is probably famous second only to pi as far as weird numbers. But pi you've learned a long time ago. It's an irrational number that goes on forever. Where does it come from? Well, in calculus is all about drawing tangent lines. So tangent line is something that touches a graph only once. And calculus is about finding the slope of that tangent line. The graph of e to the x is the only graph where when you try to find the slope of the tangent line, it's exactly the same as the value of the y-coordinate of the original graph. So that's kind of a big deal in calculus. Finding the number e, or some of you are still writing things down. Finding the number e comes from doing this. If you started with x is 1, do you see that you would get 2? If I'll make a x is 1, my answer, make this y, is equal to 2. If I plug in 2, I get 1 plus 1/2, which is 3/2, and that would be squared. 3/2 squared is 2.25. And as x gets bigger and bigger and bigger, it gets closer to e, which is a little bit counterintuitive. Because if you put in a huge, huge number, like 1,000,000, what is 1 over 1,000,000 close to? 0. And if I did 1 plus 0, I would be very close to 1. And if I would do 1 to a very big exponent, I would think I would stay close to 1. But this actually is weird. As you get higher and higher and higher, it gets closer and closer to 2.718. And that's a bit of where the number E comes from this interesting relationship.